Here we are with Unit 2 review for the EOC on reasoning with linear equations and inequalities. So we're going to go through some of the key topics. I'm just going to kind of walk through them quick and go over some vocab and other important key features for Unit 2. So we start off by solving linear equations and inequalities. It's really important that you know how to solve a linear equation. So something like this, solve 2 times 3 minus a equals 18 for a. So we're solving this entire equation. So here I see that I need to distribute first. I'm going to go ahead and distribute that 2 through. So 6 minus 2a equals 18. And then we go ahead and we solve. So we want to get a by itself, so I'm going to subtract 6 from both sides. I'm left with negative 2 equals 12. And then we divide both sides by negative 2. So a is going to equal negative 6. You can always check your answer for solving any linear equation by plugging it back into your equation to see if it's true. That's a great multiple choice strategy as well. If you are given a linear equation, you can always plug in the numbers you have for your answer choices and see which one works. Okay, we apply the same principles when we're solving inequalities. So you solve the same way. So here I have a 2 outside of parentheses. I'm going to distribute again. So 10 minus 2x is greater than 8. Then we're going to solve for x. So I'm going to start by subtracting this 10 and moving it to the other side. So 8 minus 10, that's where this negative 2 is coming from. And then we want to get x by itself. So I divide both sides by negative 2. The main difference between equations and inequalities when you're solving is if you multiply or divide by a negative number, you have to reverse the symbol of your inequality sign. So since I had greater than, it switches to less than because I divided by a negative. All right, so what happens if we go to graph linear equations and inequalities? We want to use slope-intercept form. So whenever they ask you to graph, putting something in slope-intercept form is going to be a lot easier. Remember, you can always use a table too. You can set up your x's and your y's and plug points in that way. If you forget how to use slope-intercept, you can always go back to your table. But when I start in slope-intercept, all I need is my slope, my my slope, my m, or my b, which is my y-intercept. So those are the two pieces of information we get out of the slope-intercept form. So if I have an equation like this, I'm going to start off by solving this for y. So I move the 6x to the other side by subtracting it. And then we want to get the y by itself, so I divide everything by 3. When I do that, this is my equation that's simplified, y equals negative 2x plus 3, and I pulled out my slope, which is negative 2, and my y-intercept, which is 3. We always begin with b, and that begins at the y-intercept. That's where we cross the y-axis, so here's that point. And then my slope is negative 2, or negative 2 over 1, because it's a rise over a run. So I go down 2 spots and over 1 spot. Down 2 spots, over 1 spot. That's where all those points are coming from. We do the same thing with an inequality. So here's my equation. I put it in y equals mx plus b form by solving for y. So I just add the 2x to the other side since it was subtraction. So I end up with y is less than 2x plus 2. So I pull out my slope, I pull out my y-intercept, we begin with b, I begin with my 2, and this time my slope is positive 2, so I'm going to go up 2 over 1. Okay, and you can see here if I went here up 2 over 1, you can also go down 2 and over negative 1. If you go in the negative direction, both times you're really moving in a positive direction because 2 negatives make a positive. Now, when we have an inequality, we have to take a look at two separate things. Are we going to draw a solid line or a dashed line? If we draw a solid line, we have a less than or equal to or greater than or equal to. We have to have that equals part for a solid line. So this time we only have a less than sign, so it's going to be dashed. And then since we have less than, we want to shade below the line, because it's less than. If it was greater than, we would shade above the line. And I like to just physically kind of draw in an arrow. So from the line, I point it down, and then I would shade everything underneath. Systems of linear equations. There are a couple, actually there's 3 ways that you can solve a system. You can graph a system, you can use substitution, or you can use elimination. We did a lot of substitution. This is a method that it always works. You can always plug in one of your variables into the other equation. So here you can see I've got y equals 2x minus 4. I physically pick up what the y equals, this 2x minus 4, and I plug it into the y of the other equation. So I'm just replacing this y with this entire expression of 2x minus 4. Then we simplify and we get an answer for x. Once you have one of your variables solved for, you just plug that number back into one of your original equations, and that will give you the y, or your other variable that you're missing. That gives you the point where those 2 lines cross. So here, their point of intersection, the solution, is at 3, 2. And you can see we did the same thing over here with substitution, again, in this example. And then here we used the process of elimination. Sometimes it's called the linear combination method, but this is another way in which you can find the answer to a system of linear equations. In elimination, we just try to eliminate one of our variables by making them the same value. So you can kind of see that process here. We changed this guy to a positive 3x. Okay, so I put it in the same form. It has to be kind of in that standard form. And then I multiplied this top equation by 2 so that my y's would cancel. Once my y's cancel, I'm just left with the variable of x, and then we can use that answer for x to find my missing variable of y. And you can see another example of that here. Okay, some other topics. We have literal equations. Literal equations involve taking something that has more than one variable and isolating the variable that they're asking for. So here we want to solve for x, even though we have another variable of a involved. So you can see here we moved everything away from that x. We first by subtracting 6 from both sides, and then by dividing a away from the x. So my answer to x would be 8 over a. You'll often see this when we're talking about different word problems. Not word problems, when we're talking about different formulas. So here we have an area formula. Here we have a different formula for Ohm's law, and we're just kind of rearranging it for a specific variable. Another idea from Unit 2, the rate of change. So when we're talking about a linear equation, we're just talking about the slope of something. How are my x's changing in terms of my y's? So the difference in my y's divided by the difference in my x's. That is my rate of change. So if they ask you for the rate of change, they're just asking you for the slope, and this is the formula that you use. So you have your y's, so y2 minus y1, and your x's, x2 minus x1. You simplify to get your answer. You can also do that in terms of a actual graph where your line has been graphed for you. You can pick 2 points on the graph and then use your slope formula to find the average rate of change. Some word problems that you might see here in the first one. Carla wants to save up for a prom dress. She figures she can save $9 each week from the money she earns babysitting. If she plans to spend less than $150 for the dress, how many weeks will it take her to save enough money to buy any dress in her price range? So she's trying to save $9 each week, and she wants to spend less than $150. So less than, that's where I'm getting this sign from, less than $150, and then $9, and I'm letting X represent the weeks. You could let W represent weeks if you wanted, and then we just solve. So I'm going to divide both sides by 9 because I need to undo the multiplication that we have here. So X would be less than 16.7. Okay, so it's going to take her about 16.7 weeks to save for that dress. Another example, the band is selling wrapping paper for a fundraiser. Customers can buy rolls of plain wrapping paper or shiny wrapping papers. We've identified here we're going to let X be shiny and Y be plain. You could use S and P if you'd like. The band sold a total of 55 rolls and they made $950. So if a roll of plain costs $14 and a roll of shiny costs $20, how many rolls of each did they sell? Okay, so here you'd have to set up a system of equations so that you could find out how many shiny and plain you have. I know the total number of rolls was 55, so if I add shiny plus plain, that's going to equal 55 total. I also know how much they cost. It was $20 for a shiny roll and $14 for a plain roll, and they made a total of $950. Once you have your two equations set up, you can go ahead and use substitution or elimination like we did up here to find that answer. Again, I'm not going through all of the details here. I'm just kind of giving you a brief scenario of the topics included in each unit. Next, we have identify and evaluate functions. So remember, when we're identifying functions, each input can have only one output. So here, none of my inputs repeat, so this would be a function. Here, I have an input that repeats of 4, and they're going to different outputs, so this cannot be a function. You can also use the vertical line test when you're given a graph. If your vertical line only goes through the graph at exactly one point anywhere on the graph, it is a function. If it were to cross the graph in more than one place, then it would not be a function. When we go to evaluate a function, we simply are given what x equals and we plug it in. So instead of saying like y equals 2x minus 1, we use function notation. We typically say f of x. So here we're trying to find f of 7. So we're asking when x equals 7, what is the value of my function? So I just simply plug in 7 for x and I simplify. So f of 7 would equal 13. Here, if g of 6 equals 3 minus 5 times 6, what is g of x? So g of x would just equal 3 minus 5 times x. Okay, this is how we would write it as a function. All right, so next we have arithmetic sequences. This is a linear sequence when we have an arithmetic sequence. We have two different types, explicit and recursive. This formula, or both of these formulas, are on your EOC review guide. On your formula sheet on the actual exam. So my explicit formula is a sub n equals a sub 1 plus n minus 1 all times d. Okay, and they put the d in the back, but really you can pretend like it's in front. You'd still just distribute. You need to know that a sub 1 is just the first term in your sequence, and d is the common difference. My recursive rule is a sub n equals a sub n minus 1, or the previous term plus the common difference. So here, if I was going to write either of my formulas here, if I wanted to write my explicit formula, my common difference, we take the second term and we subtract it from the first term. So 6 minus 2 gives me 4, 10 minus 6 gives me 4, 14 minus 10 gives me 4. You're adding 4 every time. That's my common difference. My first term is 2. So those are those two pieces that I need. So a sub n is going to equal a sub 1. There's my a sub 1. That's 2. Plus my common difference, which is 4. Times n minus 1. And then we just multiply that 4 through, we distribute it. So 4n minus 4. And a sub n equals negative 2 plus 4n. That's going to be that simplified. That's my explicit rule. And you can see that looks just kind of like a linear equation would. Y equals negative 2 plus 4x. It's the same type of thing. Recursive, this is finding, I'm using the previous term to help you find the next term. So here the a sub n minus 1, the previous term, that doesn't change. You just plug in the plus 4 at the end for the common difference. And then lastly, characteristics of functions. We can talk about all sorts of things when we talk about functions, things like the domain and the range, the x and the y intercepts, the rate of change. So here it says that the company takes, it takes a company 6.5 hours to set up the machinery to make engines, and it takes 5.25 hours to manufacture each engine. So we want to write a model for the production of engines, then determine the domain and the range, the x and y intercepts, and the rate of change. So I want to write a function for this situation. So the machinery takes a total of 6.5 hours. That's a one-time setup. Okay, so that's at 6.5. But then it takes 5.25 hours for each engine. So 5.25 times x, that's going to be however many engines we're building. Okay, so there's my equation. Okay, so we know that from an equation y equals mx plus b, the number with the x is my slope. That's my rate of change. My y-intercept is always that b term, so that 6.5 is my y-intercept. Okay, my domain, I can plug in any number I want for x, okay? Right, I can plug in 0, I can plug in 0 would be I have no engines to build. 1, I'd have 1 engine to build. 5, I'd have 5 engines to build. But it wouldn't necessarily make sense if we had, let's say, a number of -3, because we wouldn't have -3 engines, right? We'd only have a positive number of engines. So we have all positive values of x for our domain. So then if we're only plugging in positive values for x, we're only going to get positive values for y out. Okay, so that takes a look at our Unit 2, which was looking at our linear equations and inequalities.